squared equation or what we call the no time equation. So I have it highlighted down here. It says that VF squared equals V naught squared plus 2A delta X. Now, we almost always don't write the plus or minus because it's implied. We also usually don't write delta X. We usually just write X. It's also implied that that X in that equation is the displacement during the acceleration. If you want to memorize it as written right here, as highlighted with a plus or a minus, and you want to write a delta X, knock yourself out, right? But eventually most people do drop the plus or minus and do drop the delta X and just write X. And they know that that X represents the distance associated with the acceleration. Okay, I'm going to go through the derivation of this in a second. However, I want to motivate it again and remind you that the reason we have the V squared equation is this guy right here. There are going to be lots of situations where you don't have or need or not even curious about the time. For instance, if I am moving at 10 meters per second and I want to increase my speed to 25 meters per second, and I know my car can accelerate at 2 meters per second squared, I might want to know how long, the distance I'm going to have to go in my car before I reach that speed. I don't care about time. I'm not interested in how long it will take me to accomplish this. I want to know how long the roadway has to be. And so maybe it's even better sometimes to use like we are launching a jet off an aircraft carrier. Maybe our jet starts at rest and we know to like achieve liftoff, we need the jet to approach, let's say 200 meters per second. And we only have a runway of, let's say, 100 meters. Again, I don't care about time. I have an initial velocity of 0. I have a final velocity that I know I need 200 meters per second. And I have a runway that's a certain length. And then I'm interested in what's the acceleration required to accomplish that. Again, I'm not interested in time. So anytime you have a story problem in which you are given information about position, acceleration, and final and initial velocities, and you're not given time, nor do you need it, that's like kind of raising a red flag of, maybe I want to use the V squared equation. And again, if you think about this, here's our standard position equation right here, right? Classic standard position equation. And then this is the velocity equation. These are the first of the big three. These are our big two. Our velocity says that our final velocity is the initial velocity plus acceleration times time. Of course, acceleration by definition is the rate at which we change our velocity. So a rate times a time gives a change added to the original gives you the final. And again, if you look at these two, they both have time in it. So all we're going to do, and I often joke in class, is that these two equations have a baby. These two equations, merge them together, and you get the V squared equation. It is a simple substitution with a couple canceling of terms. This is not something I'm going to require for you to do. Now, it is just algebra. I guess you could call it algebra 2. But the motivation is that I'm deriving this from these two equations, which you know and love, and I've shown you either this is the definition of velocity, and then I already showed you where that equation came from. Again, the motivation is that it's a no time, and all you're really doing is taking two variables and two equations and merging them together. Again, that concept is algebra 1. That's like having two equations with x's and y's and doing a substitution and getting just x. In this case, we're getting rid of time. Okay? So we start with the position equation and the velocity equation, and we're going to take this velocity equation and we're going to solve it for time, which I did right here. Okay? This guy right here is me taking the velocity equation and solving for time. I just subtracted v naught and divided by a. I then am going to take this value for time, and I'm going to substitute it into the time here and the t squared there. So I'm going to take vf minus v naught over a. I'm going to put it in for t. I'm going to put in for t squared. Then I'm going to distribute v naught. I'm going to square this term. I'm going to distribute the 1/2 a. They all have like halves and a's, so I'm going to multiply both sides by 2a, which is where, can't get to highlight. That 2a on the left side comes from me multiplying everything by 2a, right? I'm just getting rid of the denominator. So all the a's will go away. Everything that didn't have a 2 will get a 2, and then the hows will go away. I then am going to cross out these like terms, right? This is a 2 v naught vf minus 2 vf v naught. This is a minus 2 v naught squared and a plus v naught squared, which is really just a minus 1 v naught squared. I then am going to move this to the other side, and I get this equation. And again, really, this delta x is really this x minus x naught. It is the difference between the final and initial position, which is why some people just say x, because it is just the distance, or actually, truly, it's the displacement between the two. And what I've done here is I've eliminated a variable, okay? So the v squared equation is the algebraic manipulation of our two standard things. And the question is, does this work for all scenarios? Well, what about the original two? When are these two equations true? They're true under constant acceleration. So, since we use these algebraically to make this one, then this guy is what, as the original two, also is only constant acceleration. And now we officially have the big three. The big three is the position equation, the velocity equation, and the v squared equation. And like 98% of all kinematic questions are going to be solved using those three things. Okay, just as a highlight, again, this is a delta x. It's the displacement during the acceleration. Often people say x. This plus or minus gets a little dicey because of the fact, first of all, velocity is a vector, so it can be positive or negative. However, we square these guys. And so when you square them, you kind of delete the fact whether it's moving to the right or whether it's moving to the left, because both a positive and a negative real number squared is just going to be a positive. However, think about this. If you have some v naught, whether it's positive or negative, and you square it, if this thing is a plus, you're going to make this term bigger. Thus, vf is going to be bigger than v naught. If it's a minus, then vf has to be smaller than v naught. So if your object is speeding up, in this case, I don't care about the direction, whether it's moving right and then moving faster right, it has to be a positive, speeding up. If it's moving left and then it's moving more left, meaning a bigger negative velocity, again, this has to be a positive because we know that's speeding up. If the object is speeding up, use a plus sign, make VF bigger. If we know the object is slowing down, thus we need VF to be smaller, then use a subtraction sign. Again, I'm always going to use A as a positive. That A is the magnitude of the acceleration. It's the size of the acceleration. Again, it should be very obvious when you think about plus or minus. If you need VF to be bigger, you're going to have to add something to V naught. If you need it to be smaller, you're going to have to subtract. So don't get carried away with that. It usually is very obvious in the story of whether it's plus or minus. Again, this is the algebraic definition or derivation of what we call either the v squared equation, or some people like to call it the no time equation. Okay, again, highlight positive and negative signs. Those are always squared, so they're always positive. This is a delta x, really, and some people just put a d, some people put an x. And again, it was derived using two equations that do rely on constant acceleration, so it itself relies and only is true under constant acceleration.